One of our main ideas, the electric field, is a region of space around an electrically charged particle or object which an electric charge would feel force. A point charge, like what it sounds, is a charge at a specific point. Another main idea is Newton's second law. The acceleration of a particle is proportional to the sum of the forces acting on it in the direction of the resulting force. Another component of this lab is superposition. The electric field contributed is unaffected by the charge of another particle in proximity. It also states the net electric field at a place is the sum of the electric fields of the charged particles in proximity. Matter cannot block electric fields. Coulomb's law speaks to the quantity of the force between two charged particles and is embodied by the equation. The most important things to take note of when discussing interactions between points are that opposites attract, like charges repel, and dipoles result from a disparity of charge between a neutral and charged object. The net force of zero occurs in the y direction when the gravity force balances the electric force. These surrounding forces, gravity and the electric force, act on the tape and they cancel one another out. Because we know that density is mass divided by volume, then we know that mass is just volume times density. The length of our tape is 0.2032 meters. Using these values in the equation we attained, the mass of our tape is 2.032 times 10 to the negative 4th kilograms. We can determine the gravitational force using the equation F equals mg and get the force to be 0.00193392 newtons in the downward direction or negative 0.00193392 newtons. We determine the separation distance by taking the average of our trials and obtain the value of 1.2 centimeters for our trials. As our final step, we'd plug in the meters and solve for our unknown charge of the tape and get the charge to be negative 5.647 times 10 to the negative 9 coulombs. To determine the number of electrons, we simply take the total charge that we just acquired, divide it by the charge of a single electron, and we get the total number of electrons to be 3.52 times 10 to the 10 electrons. To determine the number of atoms, we find the area of the tape and divide it by the area of an atom unit cell and get 3.8608 times 10 to the 17 atoms. To find the ratio, we find the ratio between electrons by dividing the number of electrons by the number of atoms, and we get 9.14237 times 10 to the negative 8 electrons per atom. We made a number of assumptions in this lab, which include ignoring air resistance, treating a long piece of tape as though it was a point charge with all the charge concentrated in one spot, assuming that each U-tape had the same amount of evenly distributed charge, assuming that tape was two-dimensional, and finally assuming that the unit cell of an atom is equivalent to the diameter squared. In our code, we got the magnitude of the charge on one piece of tape to be negative 5.647501394422138 times 10 to the negative 9 coulombs. I obtained the same number through my calculations. We also have a mechanism in our code which has a trial and error method for the tape charge to exhibit the relationships between different variables in Coulomb's law. If electrons had a positive charge and protons had a negative charge, instead of the charge for an electron being negative 1.6 times 10 to the negative 19 coulombs, it would instead be positive 1.6 times 10 to the 19 coulombs, negative 19 coulombs. And instead, a proton would have a charge of negative 1.6 times 10 to the negative 19 coulombs instead of its positive charge of 1.6 times 10 to the negative 19 coulombs. So what would change about our observations if we made about our tapes throughout our laboratory? Nothing much. The observations we made with our tapes and other charged objects wouldn't change all our observations because all of them were made from an outside perspective and we weren't looking at the micro interactions between electrons and protons. So from an outside perspective, we'd observe the same things. Opposite charges still attract and like charges still repel each other. It is important to handle the charged tapes as little as possible because the handling of the tape can change the original charge of the tape because when a neutral object, say our hand for example, comes in contact with a negative or positive object, our piece of tape, the charged object discharges its charge onto the neutral object and then both the objects have the same charge, which is why we often see these objects start to repel each other once they've been handled incorrectly. In conclusion, the main focus of this lab was electric fields, which we know is a region of space around an electrically charged particle or object in which an electric charge would feel a force. We also know how opposites attracted and how dipoles are created from a charged point and a neutral point, and how touching a charged object can discharge the charge onto another object. We saw how Newton's second law played a role when the electric force and the gravity forces balanced each other out. And finally, we had to take a look at what assumptions we made throughout this lab, such as ignoring air resistance in calculations, treating the tapes like point charges, using the same charge for both pieces of tape, taking our piece of tape as a two-dimensional object instead of a three-dimensional one, and taking the unit cell as the diameter times the diameter.